right, as we start our course, then the first topic that we explore is what we call limits. And I've split this into two parts. I think there's a natural split in the limit section, so I've broken it up into two pieces so that we can, I'm going to say, kind of more deeply explore each part. So the first and most important thing is to understand the definition of limit. Okay, it says a limit is if as x approaches a value c, our function f of x becomes very close to a single real number value L, then the limit of f of x as x approaches c is equal to L. One of the first things we're going to do is make sure that we're okay here on the notation. We see the LIM in front of our function f of x, so that's indicating limit. We see the x approaching c down below the f of x, that's telling us what value we're approaching. And then if the limit exists, we're going to see a real number L on the other side of the equal sign. So a couple of notes. First of all, the L is a y value. So when I say if we have a limit and it's existent, what's the limit going to equal? It's going to equal some type of y value. The second thing is that L, that y value, is not necessarily equal to the function value at x equals c. Okay, the function value would be denoted as f of c. Okay, we're going to know what c is. It'll be some type of real value x, but we're going to know what that value is. But notice that the limit is not necessarily equal to the function value. And then the third thing, and that's, I'm going to say it's kind of relating back to the second thing here, is that the function value doesn't even have to exist at x equal to c in order for the limit to exist. So there doesn't even have to be a point there for a limit to exist. Okay, so limits are kind of different ideas. We're going to be able to see better what they are when we look at a graph, but I wanted to make sure to get just some of the basics down first. Some notation. Notice here we've thrown in a couple of different things. Notice there the little minus sign almost in the exponent and the little plus sign there in the exponent. These are read the limit as x approaches 3 from the left of f of x equals 6, and the limit as x approaches 3 from the right of f of x equals 6. The 6 is irrelevant. I'm just making up some number there, but just noticing the notation. The important thing that I want y'all to notice there is if you see a little, I'm going to say, script of either a plus or a minus sign, then that's indicating that you're taking a limit basically from a particular direction, either from the left or from the right. So let's look at determining limits graphically so you can get a good idea of what limits are and what actually is happening. So part A here, we're looking at this graph. Notice that this is a graph of a function. There is one thing that I want to point out about this graph that maybe we will have remembered from algebra. Over here on the left-hand side, we notice that we have this piece going to infinity up there, and then this piece going, looks like, to negative infinity down there. That's going to indicate that you have some type of vertical asymptote. And on this one, I intend the vertical asymptote to be here at -5. So normally we would have a dashed line indicating a vertical asymptote. And I'll go ahead and add that in there so that you're able to see that that asymptote exists there. Also notice from what we talked about concerning piecewise functions, this thing is actually a function. If we looked at a vertical line test, it would pass the vertical line test. One of the breaks we would look at here and here. Notice that one point is not included while the other one is, and so we don't have any kind of issues there at the break as far as it being a function. All right, let's go back over here to part A and look at what they're asking as far as limits are concerned. Okay, here they're asking for the limit as x approaches -2 from the left-hand side of my graph. So what I'm going to do is first of all notice that for a limit you're looking down here and it's an x value, so you want to be looking on the x-axis. you're looking at the function only very, very close to -2, but specifically on this one from the left-hand side of -2. So look at what your function's doing. So here's -2. So if you think about approaching -2 from the left-hand side, only very close, what's your graph doing? So your graph's up here. Do you see it's going towards that number there? And so what you're going to want to do is that number is not important if the function exists at -2 or not. It only makes a difference what you're getting close to. And what you're getting close to is you're going to be getting close to whatever y value you have over here. So that would actually be my limit. So on this one, as I approach -2 from the left-hand side, my limit is going to end up being +1. All right, I'm going to erase my scratch work there. This is going to get messy if I leave it all there. All right, the next thing down, it asks for the limit as x approaches -2 from the right-hand side of -2. So what I'll do there is only very, very close to -2. So I'd be approaching -2. I'd be looking then at what my graph is doing. My graph is going up, getting close to that open circle. It doesn't make a difference that there's no point there. I want to know what y corresponds to that point. The y value that corresponds to the point is the number there. So my limit would be 1. All right, so I've basically got a limit as I approach 2 from the left, -2 from the left being 1, and a limit as you approach -2 from the right being 1, which is going to basically mean that my overall limit as I approach -2 is also going to be 1. When you take an overall limit, you have to look at what happens to your function both from the left, my function's approaching that, and from the right, my function's approaching that. And if you think about it, you're approaching the same y value of 1. And so if you approach the same y value, then your overall limit is existent, and it exists and matches whatever you have here. Okay, so that's a very basic idea of a limit. Now notice here that f of -2 is not even defined. So not defined, or you might even say does not exist. And that's okay. I'm going to come back up here and notice that what we said on number 3, the function value doesn't have to exist in order for the limit to exist. The limit is only what you're getting very, very close to as you approach your x value. All right, let's hop down to part B. Part B says we're looking at the limit as you approach 0 from the left to begin with. So looking at 0, 0 would be here. So as you approach 0 from the left-hand side, you're looking at your function. You'd be looking at this piece of your function. So your function would be getting close to that value there. To know what piece you're looking at, remember that you're only looking at 0 very, very, very close to 0. And so you're not interested in, let's say, this part of the function out there or this part of the function out there, because you're only looking at a very small piece of your function. So you can kind of think of it as looking at it under a microscope. If you are looking in or you're honing in on 0, you're only wanting to look at the piece of the function that's near 0. Okay, so if we approach 0 from the left-hand side, it looks like my function is actually approaching -3. So that would be the y value there. So this value would be -3. All right, let's now look at what happens as you approach 0 from the right. So approaching 0 from the right, you'd be really, really close there. Notice you're no longer on this part of the function, but you're on this kind of V-shaped, and you're coming in this direction. So as you're coming in this direction on your function, you notice your y value is getting close to -1. So the limit as you approach 0 from the right is -1. That means that the overall limit is not going to be existent. As we approach 0 from the right, it's getting close to -1. As we approach 0 from the left, we're getting close to -3. And notice that those two y values aren't meeting up. So these two don't match. You basically have a break in your graph. And because they don't match, this here does not exist. Now, remember we said the existence or non-existence of the actual function value at the number doesn't make a difference. Notice here, f of 0, they're asking us for the function value, specifically at 0. If you plug 0 in, notice this is the point that's closed in, so f of 0 is -3. It doesn't make a difference that the function value at 0 is -3. Notice that our overall limit didn't exist. All right, the next part, let's look at part C. And I'm going to erase. No, actually, I think I'm going to leave that. I'm going to just change colors maybe for part C. All right, so on here for part C, we're looking at -5 from the left. So as you approach -5 from the left, so we're on the x-axis, you're approaching -5 from the left. What part of the function are you on? You'd be on this part up here. So notice here that that function's increasing without bounds. So I mean, it's going up and up and up. Now it's getting close to that vertical asymptote, but it's going, I'm going to say up without bound. That means here that this limit is approaching positive infinity. All right, let's look at the limit as you approach -5 from the right. So as you approach -5 from the right-hand side, what part of the function would you be on? You'd be on this part down here. Notice it's decreasing without bound. So that would be negative infinity. Okay, now if we ask for the overall limit as x approaches -5, notice that from the left you're going to positive infinity, but from the right you're going to negative infinity. You're approaching two different things, and so here this does not exist. Now, when you're dealing with infinities, it's a little bit tricky because an infinity automatically means that your limit is non-existent. Remember that up here in the definition that our limit has got to be a real value. Obviously, an infinity is not a real value, so it's indicating that my function's growing or shrinking without bound, but an infinity actually also means that the limit is non-existent because it's not approaching a real number value. Okay, and I'll show you that here in a little bit with part D. I'll show you a little bit more there what I mean. And we'll actually see another example later on that will hopefully help you with infinities. Now on here, f of -5, it was important that at -5 there's a vertical asymptote. So that means at -5 my function is not defined. Okay, or my function does not exist at -5. Okay, once again, the existence or non-existence of a function though at that value that you're interested in your limit is not actually important. All right, let's look at part D. Part D, it says we want to look at the limit as I approach 3 from the left. So coming over and looking at 3, let's approach 3 from the left. That means I'm on this part of the function. Okay, what value am I getting close to as far as my y value? Looks like I'm getting close to 1 again. So the limit as I approach 3 from the left is 1. How about the limit as I approach 3 from the right? So as I approach 3 from the right, the function has that behavior. Y'all notice here that my arrows are meeting up. Notice that that function value is 1 again. Notice that these two things match, so the overall limit as I approach 3 is also 1. Notice here that the function value is 1. So in other words, that actual point was filled in there. Here, this is a situation of what we called a well-behaved piece of the function, meaning there's no vertical asymptotes, there's no breaks, there's no holes, everything meets up nicely. And that actually means that your function value and all your limits at that particular location of your x's should be equal. That's not always going to happen. That's actually somewhat of a rarity when we ask function or limit type questions, because generally with limits, we're interested in limits, let's say like at a break or at a hole or an asymptote or something along those lines. All right, I hope that this helps you. If you have any kind of questions concerning limits graphically, make sure you shoot me an email and I can help you on a more individual basis as you have those questions. All right, the next thing I'd look at is 2 ways that a limit can be non-existent. So it's nice to know when you're not going to have a limit existing. Okay, the first way is if the limit as you approach c from the right-hand side of your function is not equal to the limit as x approaches c from the left-hand side of your function. Generally in a lecture class, I use my hands to show this. So in other words, if you can think about your left hand and right hand on different levels going toward each other, you can see they're not going to meet up. There's going to be some sort of break in your graph. Okay, so if there's some sort of break in your graph, then you have your limits being non-existent. The other thing that can happen is that the limit as x approaches c overall, that means you're going to look at it from the left and from the right. Okay, that means that if you look at a limit and your limit is either equal to positive or negative infinity, that's going to indicate that there's a vertical asymptote at x equals c. And if there's a vertical asymptote at x equals c, then you're going to have a non-existent limit. You may say what the limit approaches, but your limit is still going to be non-existent. Okay, I'll help you see that down here on an example here a bit. All right, they want us to draw an example of two different graphs where the limits as x approaches 2 specifically does not exist. So as a first example, let's think about number 1 up above, a graph where we have a break specifically at x equals 2. So we're going to come over here and label 2. We want to make sure we have a function. So here we go with a function. I'm just going to make this linear to be easy. I'm going to put an open circle there, stop it at 2. And then let's say that we have a closed circle here and we have something horizontal that direction. So we notice here that at 2, as you approach 2 from the right hand side, you'd have a y value here. Let's call it y1. As you approach 2 from the other side, you'd have a different y value, let's say y2 there, and because you're not approaching the same value, then your limit would not be existent at 2. All right, and the second way, I'm going to think about number 2 up here, a vertical asymptote at 2. So there, if I draw a graph, and at 2, we make sure we put a vertical asymptote, that means that the behavior of my graph, traditionally these have kind of little C-shaped behaviors when you have an asymptote. Let's say we draw something like that. And you guys neither, I'm going to say, if one student's doing this and another student's doing this, they're not going to look the same as far as your graphs are concerned, but they're going to have similar characteristics. In other words, one student drawing graph number 1, you may have your lines in different places. You may have a parabola on the right-hand side as opposed to a horizontal line, but they're both going to have breaks at 2. So if one student's doing it and another student's doing it, you're both going to have a break at 2. Same idea here over here on the one where I'm doing the asymptote. You're both going to have asymptotes at 2, but your actual shape of your graph may look differently, and that's okay. Okay, so this is, I'm going to say, the kind of tricky part about limits. Sometimes limits are non-existent, but we can specify how they don't exist. So let me explain using these two examples. So for number 1, it says find the limits for the graph below. So we want to look at the limit as x approaches 0 from the left. So as you approach 0 from the left, you see your graph has a downward turn. It looks like here we have a vertical asymptote at 0. So on here, we're going to say that that graph is approaching negative infinity. When we write that down, we mean that our function doesn't exist because it's not approaching a real number value, but we can say, hey, it doesn't exist, but has the behavior that it's negative unbound. Same thing as we approach x from the right. So if we approach x from the right, we notice that our function is going downward. So we can say it's negative infinity. And then if we looked at the overall limit, as we approach both from the left and the right, we notice that our function's doing the same thing. So we're both approaching negative infinities. So we're going to say the overall limit's negative infinity. Now that means that it doesn't exist, but it doesn't exist in a negative downward behavior. Okay. For the second piece, it says find the limits. So same idea here. It looks like once again we have a vertical asymptote at 0. If we look at the limit as x approaches 0 from the left, looks like we have a downward negative type behavior, so negative infinity. your limit doesn't exist, but you're saying it's negative infinity to indicate its behavior. So by the way, if you're working on a problem in the homework or on a test or on a worksheet, quiz, then you're not ever going to want to tell me that this does not exist. So an incorrect way to write this would be does not exist. You don't want to tell me that. You want to tell me that the limit is negative infinity. I know and I understand that that's telling me two things. It's telling me that it's not existent, and it's telling me how it's not existent. All right, now, as I approach 0 from the right-hand side, we can see there, as we approach 0 from the right-hand side, my function is going up without bound, so it would be positive infinity. Now, do these two things match? They don't match. So if these two things don't match, then you're always going to tell me that the overall limit does not exist. Okay, so the difference between these two examples is, even though over here everything was non-existent, these guys do match, which means when you come down here to the overall limit, you're going to tell me, hey, it doesn't exist, but it doesn't exist in this way. And then here, you're going to tell me it just does not exist overall because you're approaching different things from the left and from the right. All right, the next topic I'd like to look at is determining limits, not graphically, but using a table. And it's almost the same thing, but you're using a calculator to look at the values as opposed to looking at a graph. All right, the first thing I'm going to do is tell you that for this particular course, I'm going to use a TI-84 calculator, and that's the steps that I have here. The TI-83 calculator or TI-84 calculator, it doesn't matter what addition you have. Generally, the steps will be the same for both. For the 83, it's a little bit older of a calculator, so sometimes you have to do a little bit more. If you have any questions on anything on a calculator, always let me know. If you're using TI Inspire, make sure you realize it cannot be a CAS model. But generally what you can do is you can Google. So on here, we're making a table. So what you could do is for the Inspire, you can Google, create a table, and then it can give you instructions on what to do on your particular calculator. All right, so for this example, I have f of x equals to square root of 1 minus x minus 2 all over x plus 3 as the function. I definitely don't want to try to graph that. That's going to be something that I don't want to graph by hand. It wants us to find the limit as x approaches negative 3 of f of x. The first thing is when you enter this particular function on your calculator, it is very important that you put parentheses around both the numerator and the denominator, or else it won't graph it in the proper way. All right, I'm going to use WabbitMove, which is basically an app that's a TI-84 calculator, and then I'm going to run through this particular problem using that calculator. So the first thing I'm going to do is pull up that app, and then I'm going to enter that function, and then I'm going to come back to the notes. So in the calculator, turn your calculator on, and then we're going to go to the y equals menu here, and we're going to start with a parentheses, and we're going to type in the top. So it's second square root, and then 1 minus x. I have to make sure to close the parenthesis around the square root, and then also close the parenthesis around the top, and then divide by parentheses, and then it was x plus 3 on the bottom, so x plus 3, and then close that off. All right, so now that I have that entered in, I'm going to go back over here and see what the instructions told me to do. So it says to enter the formula, we've done step number 1, so we're good to go. All right, it said set second window and set up the independent variable to ask. All right, so this is setting your calculator up so that it will allow you to plug in x values as opposed to picking your x values for you. So we're going to second window, and then the independent variable needs to be set to ask. So arrow down, and then arrow to the right, press enter over ask, and then we're good to go. All right, going back to the notes. All right, it says press second graph and then enter appropriate x values to determine your limit. All right, so on here, what I'm actually going to do first is I'm going to determine those limits. You see I have a table, I'm sorry, those x values. I have a table down here below. Notice that we're wanting to do a limit as you approach -3. So I've put -3 in, and then also I've blocked out -3. You don't ever want to actually plug in the function value. Remember that a limit is based on what you get close to as your x approaches that x value, but you don't care what the function value is at that particular value. All right, now on negatives, be careful. So I want to approach -3 both from the left and to the right. And I want to do so using numbers that are very, very close to -3. So let me do it this way. If you're trying to approach -3 from the left-hand side, then you'd be looking at values like -3.1 or -3.01, things like that. So what I'm going to do is I'm going to use -3.001 there. That would be very close to -3. And then I'm going to back off a little bit. So I'm going to do -3.01. And then I'm going to do -3.1. What you can always do is insert. So like if your table doesn't show you what you need, you can always get closer. So you could do like -3.0001 or something along those lines. Okay, so if you need to alter your table, we can definitely do that. And then to the right of -3, you're going to be looking at values like -2.9 and -2.99. The important thing is that you do these, I'm going to say, in order from left to right. So let's say I do -2 and then do 999. Generally, like over here, I'm using 3 decimals, so over here I'll use 3 nines. And then -2.99, and then -2.9. So whatever you do, make sure that as you look from left to right, all of these are in order. It's the most important thing. So those are the x values that I'm going to end up using. So let me come back over here to my calculator, and we're going to enter those x values into my table. So we do second graph to get to my table. And I'm going to start with my leftmost x value, which was -3.1. Press enter. So I got -20.25. And I'll record these here in a little bit into my problem. Let's double check something right quick. Let's go to y equals. Let me make sure I have this right. I don't. There's something wrong with what I had entered in. Here under y1, I have square root of 1 minus x. Notice in our problem, we also had a -2 that was on the outside of the root. So I need to come in here and fix that. So I'm going to go to that parenthesis and then do second insert and then do -2. So on this one, you wouldn't necessarily have any way of knowing unless you went back and double checked that that value that we got out was incorrect. But I knew that that wasn't the right value, so I knew something must be wrong somewhere. So that is a good thing to do. When you make a mistake, I'm going to say if we suspect we make a mistake, the first thing to do is go back and make sure that your function is plugged in correctly. In this particular one, also make sure you have parentheses around your numerator and denominator, which they do, but we had just left out the -2. So now if we go back to our table, so second graph, it will automatically adjust that value to us. So like a while ago it was 20 point something, now it's -2.485. That's the correct value. All right, and then let's do the next x value. So it was -3.01. And then the next closest was -3.001. So we're approaching -3 from the left-hand side. And do you see here, as we approach -3 from the left, it looks like we're getting really, really close to looks like 0.25. So it was -0.2485, and then it was -0.2498, and then it was actually -0.25. So now we're going to go to the right-hand side, but make sure you remain in the same order. So we're going to literally go through our table from left to right and enter the numbers. Whatever you do, do not enter a -3, which is the actual value that we're trying to approach. So the next closest value was the negative 2.999. Look what we get there. We get negative 0.25. That makes me fairly confident that my limit is going to be negative 0.25. Okay, let's go a little bit further away. So negative 2.99. It's negative 0.2502, so it's a little bit further away from negative 0.25. And then negative 2.9. And a little bit further away. But do you see, we're interested in specifically this number here in the middle when you're really, really close, and that number there in the middle is matching up. Now, if the number doesn't match up, you can do what I mentioned earlier by putting more zeros. So like you could have another number in here, and it could be negative 3.0001, and then you could put another number here. It could be negative 2.99999, and then that way you can be more confident if you're not sure about your answer. On this one, we're fairly confident. All right, so let's write those values in that we got here. I got negative 0.2485, negative 0.2498, negative 0.24, negative, I'm sorry, that's supposed to be 5. Negative 0.25, negative 0.25, negative 0.2502, and then negative 0.2516. All right, and notice here what I said before, you want to do these in order on your table from left to right. You don't want to work your way this direction and that direction. That's not going to work well. All right, so on here, step number 4 said we've basically done these 3 things. Step number 4 said make sure to write your final answer and to indicate the value of the limit. So basically here, your table is only meant to be scratch work. You've got to say at the end, so the limit as x approaches negative 3 of f of x appears to be equal to negative 0.25. And on this, if you want to, obviously negative 0.25 is negative 1/4. If you want to write that instead, then we definitely could. Now be careful, you may also run into problems where they don't meet up in the middle. So if they're not meeting up or they're not getting close to meeting up, they may not be exact, but if they're not even getting close to meeting up, then it's probably a good indication that your limit does not exist. All right, so computing limits algebraically, this will be the last group that we'll look at here in part 1 of limits. I said make sure that you keep your limit notation until the step when you actually plug a c value in for x. That's one of the most important things as far as your work for limits are concerned. Here are your tools. Your tools are, first of all, direct substitution. This happens when you have a nice, well-behaved function in or close to the particular x value that you're looking at. So here we're looking at x approaches negative 6. We have a rational function. Remember, we looked at domains of rational functions, and we said the denominator couldn't be 0. So like on this particular problem, at x equals 4, we have a problem because the denominator would be 0. But notice that the x value that we're approaching is nowhere close to 4. So because it's negative 6, that's not going to cause us any kind of issues. So we can directly substitute negative 6 in for the x values. That means we're going to lose the limit notation immediately, and we're going to plug in 5 times negative 6 plus 3 all over negative 6 minus 4. And then just simplify that out. So negative 30 plus 3 all over negative 10. We need to do negative 30 plus 3 first, so negative 27 all over negative 10. And then there, the negative divided by negative would be positive 27 over 10. I don't need you to change that to a decimal. It's reduced completely, so that would be your final answer. Okay, the next one down, we have a square root. Remember on roots that the value underneath the root has got to be positive. Well, on this one, if we look at the number that our limit, we're indicating that we're approaching in our limit, it's 2. Think about if you plug 2 in, it looks like plugging 2 in is going to give you a positive thing underneath the root. So I don't think we're going to have any problems here. So if you don't have any problems, you can just take this x value and plug it directly in for your x's and get rid of your limit. So 10 times 2 minus 4. We're getting rid of our limits immediately because we're plugging in immediately. So we're going to have 20 minus 4 under the root. So that will give us 16 under the root. Square root of 16 is 4. No problems. All right. Next thing is we're going to look at factoring and reducing. A lot of times when you have rational functions, we have problems. Not always, but sometimes. So like we looked up here at this rational function, we didn't have any problems on this one because we were going x approaches -6. That wasn't an issue. However, if we had done x approached 4, that would be an issue. Okay, so on this particular one, let me look first at what would happen if I plugged in -1. If I plug -1 in specifically down here on the bottom, and you don't need to copy this into your notes, you can just watch for a second. If we plug -1 down in here, this will be 2, that'll be 1, that'll be +1, -3. So 2 plus 1 minus 3, that's going to be 3 minus 3, that's 0. So the first and easiest thing to do is see if you can actually plug your value in. Plugging your value in here would result in 0 in the denominator. That's a bad thing. So if that happens, you go back and you erase all this work you've done. You say, that is not what I need to do. Now, the one thing I need to tell you is just because you plug in your value and it results in something bad doesn't mean your limit doesn't exist. That just means you're not going to do your limit that way. And so on here, if you have a rational function and plugging in results with 0 in the denominator, one of your tools is you're going to try to factor whatever you have and reduce it. So we're saying the limit as x approaches -1 of x plus 1 over 2x squared minus x minus 3 is going to be equivalent to the limit as x approaches -1 of the x plus 1 on the top is already factored, so we're going to leave that. And then we're going to try to factor the bottom piece. It's a trinomial with not an understood 1 here in the front, so we're going to have to use guess and check. So we'll use a 2x here and an x there to give that 2x squared. And then go to the back, we need a 3 and a 1 it looks like. So let's say if we put the 3 here and the 1 there, I don't think that's going to work as far as our middle number being a -x. So let's try putting the 3 here and the 1 there. Notice there we want to have a negative. So if we put the negative with the 3 and the positive with the 1, notice the inner product is -3x. The outer product is 2x. That will definitely give me my -x. So we're good there. I'm going to erase that scratch work for my factoring. All right, now notice that when you factor, you now have a factor that's the same top and bottom, and we can reduce that factor. Now reducing cancels to a 1. It's important that on the top we leave a placeholder of 1 since there's nothing else up there. And so this reduces to limit x approaches -1 of 1 over 2x minus 3. Okay, now notice that I've kept the limit in front on this step and on this step because I have not yet plugged in that x equals -1. So you want to make sure to keep that limit all the way up to the point of your plug-in step. Okay, now let's see what happens if I plug -1 in for x in the problem now. So if I do that, the limit disappears. I have 1 over 2 times -1 minus 3. That looks good. So 1 over -2 minus 3. 1 over -5. Nothing bad happens. Okay, what happens is there, we basically got rid of the problem when we canceled out that x plus 1 factor, and then that left us something that we were able to evaluate. So the original function turned out to actually not be defined at -1, but we were able to reduce it to something that was equivalent everywhere except at -1. And so by doing that, we were able to find our function value. So remember what I said earlier about just because you plug in the value and it gives you 0 in the denominator, that doesn't mean that your limit doesn't exist. It means that you're not going to evaluate your limit that way. I'll also tell you something else as far as grading is concerned, specifically on your midterm or even on your final. You never, ever, ever want to leave me something that has 0 in the bottom. Okay, so if you're going through and you're doing limits and you end up with 5 over 0, then you want to erase that. You want to back up and you want to do something different. You won't get any kind of credit if I end up seeing something over 0 as far as that's concerned, because you cannot divide by 0, and that over 0 doesn't necessarily tell you anything as far as the limit is concerned. All right, let's try that again with this problem down here. Notice here that if we actually plugged in x equals 5, that would give me a 5 squared minus 25 on the bottom, which would result in a 0. So that wouldn't be good. I'm not going to do that then. So I know my trick is to factor and reduce. Make sure you keep your limit notation. All right, the top is a trinomial, understood coefficient of 1 in front of x. So I should be able to use an x and x, and then I need a factor of 45 that would add to 4. So factors of 45, I think I could use a 9 and a 5. If I made the 9 positive and the 5 negative, I'd get negative 45 at the back, but I would have adding to the positive 4 there in the middle. And the bottom is a difference of squares. This looks like x plus 5, x minus 5. And then notice here that once again, you have 2 factors that will cancel. So you're reducing this to limit as x approaches 5, x plus 9 over x plus 5. And then you're able to go ahead and plug in. So notice that we kept our limit here and here. And then at this point, we're going to drop the limit when we actually plug the 5 in where our x's are. Okay, so on the top, we have a 14. On the bottom, a 10. That's reducible by 2. So if I divide by 2, top and bottom there, I'll get a 7 over a 5. And then that would be the value of my limit. All right, we have one additional tool in our tool bag as far as ways to evaluate limits. And the last one is if you end up with some sort of a root in part of your limit and you're trying to plug in and you get 0 in the denominator. So like on this one, you'll notice that we're approaching 36 for my x's. If I plug 36 in the denominator, I get 36 minus 36, which is 0. But also notice that I have a root up here in the top. There is this thing that's called a conjugate. So if I want the conjugate of, it keeps zooming on me here. Give me just a minute. So conjugate, apologies. All right, so the conjugate of square root of x minus 6 is square root of x plus 6. So what you do is you keep your root and your value the same, but then you change the sign in the middle to, I'm going to say, create a conjugate. So if you run across a problem like this, what you do is you multiply the top and bottom both by the conjugate of the root. So we would multiply top and bottom here by square root of x plus 6. Now, this is what I call a sink or swim problem, meaning you're on an exam or you're on a quiz, you either know to do this or you don't know to do this. And if you don't, that's very dangerous because the likelihood is you're going to come up with this is probably slim. Okay, you may remember it, that'd be great, but to actually come up with it on your own if you don't remember, that may not necessarily happen. All right, so from here, what we do is we now multiply, or we FOIL the top and the bottom. So on here, if we're FOILing out the top, then what we do is we multiply the first and the first. Okay, now keep your limit. So we haven't evaluated at 36 yet, so it's important we keep the limit. We do square root of x times square root of x. That's going to be the square root of x squared. And then we do the outer. Okay, that's square root of x times 6. So what you do there is you say that's going to be 6 square roots of x. And then you do the inner, -6 square roots of x. So you can't actually multiply the 6 and the x, and the 6 is outside of the root and the x is underneath, so you keep it that way. And then you do the last, -6 times 6, -36. So there's the top. Now, the conjugates will always multiply out and simplify a particular way. So here in a bit, I'm going to tell you I don't mind if you skip a step when you're multiplying the conjugate part. Now, the bottom part you're going to leave alone. Okay, so the top part you FOIL, and the bottom part you leave alone, meaning you're going to leave it completely factored. And the reason that you're doing this is the part that's causing us problems is that part right there. I can't plug the 36 in without that being 0. So if I keep it factored, then here in a bit my hope is I can make that x minus 36 factor cancel. If I multiplied it all out, then that factor is going to get lost. So you want to make sure to keep that bottom part factored completely. That saves you a step, and then also later on will result in what you want to have happen. So we have limit x approaches 36. We're keeping that because we're not plugging the 36 in yet. And then notice what happened when you FOIL the conjugates out. You have a +6 roots of x and a -6 roots of x. That's always going to happen. So when you multiply the inner product here and the outer product out here, you're always going to end up with 2 terms that are opposite in sign. That means you can literally get away with multiplying a conjugate by multiplying the first 2 terms and the last 2 terms. So essentially there, if you did that, you're going to get root of x times root of x is just going to give you x, square root of x squared. And then -6 times 6 would have given you -36, which is what I get from reducing the numerator from my actual FOIL step. And then we're leaving the bottom, x minus 36 and square root of x plus 6. Now notice the top is a factor that's going to cancel with that bottom factor. Make sure to remember there to put a 1 to hold place since you've canceled out the entire numerator. We're still going to keep the limit as x approaches 36 because we've not yet plugged in 36. We have a 1, and then we now have only left root of x plus 6 in the bottom, and then now we can plug in. So 1 over square root 36 plus 6. We remove the limit, and then we can reduce. Square root of 36 is just 6. 6 plus 6 in the bottom is 12, so this becomes 1 over 12. All right, y'all make sure to email me if you have any kind of questions.